Okay, so how does the pooling via SLMA work? Basically, it's based on a function called dsglim SLMA instead of the original dsglim function that we discussed earlier. And basically, the AC client basically calls dsglim SLMA specifying what model is to be fitted. And the dsglim SLMA then calls three server-side functions that collectively request each study to fit the requested glim to completion, i.e. all iterations of process until convergence occurs. And then once convergence has occurred, the estimates and standard errors from those completed models will then be returned to the AC. The AC client will then combine the estimates of those regression coefficients using the standard errors as well in order to enable a random effects or fixed effects meta-analysis. Now, crucially, if we now want to add an unanticipated interaction, all we have to do is change the regression formula, in this case, the change of a single character, and then fit the model again. So this basically takes seconds, not days or weeks. This is clearly a useful role for DataSHIELD. Okay, let's look in a little bit more detail at the actual structure of DataSHIELD and the way that it's actually been implemented at the current time. So if we look at the diagram in the bottom right, we can see a number of elements of this structure. The first one can be considered to be me sitting at my laptop, so I'm the researcher. And in this particular architecture, this is basically just being used as a dumb terminal. And this dumb terminal is connected to a DataSHIELD client portal, or in fact, really it's connected to an RStudio sitting in the DataSHIELD client portal. And in this particular instance, as an actual practical example, when DataSHIELD was originally developed under the BioShare EU project, which was a Netherlands-based EU project, that DataSHIELD client portal with its RStudio was sitting in Groningen in the Netherlands. So basically, I'm logged into the RStudio in Groningen, and I'm going to be sending commands via the green arrows out to the various studies in order to enable the analysis I want to take place to occur. Now, let's look at the structure of what's happening at the different studies. So in each study, first of all, before DataSHIELD was set up, they obviously had their data sitting in some data warehouse, and there's no particular requirement that the data warehouse 1, 2, and 3 need to be the same in any way whatsoever. However, what will have happened is that the data that wants to be shared, that will need to have been transferred to a data table in an Opal database that is sitting by that server, by the original warehouse behind the same firewalls. Now, crucially, the Opal database is the databasing system developed by our main informatics partners on the DataSHIELD project, who were called originally Abiba. They're part of the Maelstrom group in Canada, and now are based in France under the name Epigeny. Okay, so their database Opal is set there. The data that's to be shared has been passed out from the data warehouse into the data table. And the data from that data table now need to pass into the an R environment that's sitting at each of the studies. So this is again shown by the cogwheel in each of the studies. Now, that step is in fact the first command that is issued by the DataSHIELD client portal. So the DataSHIELD client portal that I'm controlling as a researcher says to each Opal server, please transfer your data from your data table into a data frame on the R server. So that transfer occurs. Now that data then is now in our environment, and I'm now in a position to send our commands directly to it. Now that R environment is very unusual in that the only way that any commands can be sent into that R environment are through the DataSHIELD client portal and the Opal. So the R server is actually embedded, sorry, the R environment is actually embedded in the Opal server. And in order for commands to get from the DataSHIELD client portal into the environment, it has to pass through an R parser, and that R parser checks both the characters that are being put into this string of command that's coming across, and also check that the functions that are being requested are valid DataSHIELD functions and have arguments that are consistent and valid under DataSHIELD. So basically those commands then go into the R environment. In the environment, they are basically calling the server-side DataSHIELD functions. Those server-side DataSHIELD functions do the analysis that's required and do one of two things. They either write the answer into the R environment on that Opal, if it's an assign function that you're calling on the server side, or they send results back to the client portal and then to the researcher if it's an aggregate function that's being called. So basically, if it's aggregate functions are being with results returned, the DataSHIELD client portal will then combine them in whatever ways requested across the different studies, as we've seen already in this talk, and then we basically have the results that are needed by the client and the researcher in order to proceed with the analysis. Okay, so that's the basic setup, which is now being used many times over numerous studies. Okay, let's just slightly in more detail consider the disclosure controls that are built around DataSHIELD. So this is multi-layer, as we've said. So the first thing is that before setting up an instance of DataSHIELD, you don't just want to set it up in a very fragile IT environment where there's very little in the way of disclosure control anyway. DataSHIELD should be built onto robust hardware, and for example, all transmissions going outside DataSHIELD should be encrypted in standard ways, and this system should, for example, be robust to hacking, etc. At the same time, as well as the hardware being robust, in general, DataSHIELD should only be set up in situations where you've got good formal governance agreements in place. And so, for example, one of the things that you should have permission to do is to use DataSHIELD on these particular data. So basically, we need good hardware, good formal governance agreements, and so this is the same as any other approach to analyzing data that you would have. Now, what about the controls that are specific to DataSHIELD? So first of all, we've already seen that the server-side R can only be called via the Opal. So basically, you cannot do anything to the data sitting in that server-side R unless you're sitting on the client portal and are able to send commands, valid commands through. Secondly, we can check that those commands are valid and that there are no other illegal characters in what's being passed through, because everything has to go through the R parser. Then when the commands reach the server side functions basically are designed so that they don't allow any disclosive output. So, for example, there is no print function on the server side, because if there was, that would simply print out all the values of a variable, which is clearly what we're trying to avoid. But to be a bit more sophisticated, every time we introduce a new function, for example, the glim function, then basically the standard glim function in R returns a variety of things, including the regression residuals and the fitted values. Now, if those were passed back to the client, it would be possible for those to be combined to get the actual observed outcomes in every individual. And therefore, the dsglim server-side functions that are called are basically stripped of their residuals and their fitted values before being passed back. So basically, every time we introduce a new server-side function, we have to think about whether or not we need to delete elements of what's happening. So then, to go beyond that, we also then add disclosure traps. So as the function is running on the server side, each time it comes to a particular issue that could cause a disclosure problem, then if necessary, a disclosure trap will have been sent. So good examples of that are, as we've already seen, the minimum cell size in a table. So the server-side table function has a trap that looks at the size of all the cells in that study, compares it to the minimum cell size allowed, and if it's too small, then the whole table is blocked. Similarly, the test of GLIM saturation, so how complex a generalized linear model will be, is part of the server-side GLIM function. And if that's trapped, then the whole GLIM model will be stopped. So basically, we've added to the rules about the parser, we've added these disclosure traps to then add extra levels of security. And a key point about the trap thresholds is that these are all set at the server-side end, and they are solely under the control of the data custodian. So the analyst cannot modify those trap thresholds. The final level of security is that all commands and outputs that are requested by DataSHIELD are logged as commands and output on the remote servers. This means that if anybody tries to get around traps, for example, by running sets of simultaneous linear equations, this can be identified as having happened. And this therefore allows the potential, if the governance agreements are correct, to formally review the instructions that have been used by a particular analyst if there is a concern that a disclosure event's occurred. And if then we can demonstrate that there has been deliberate malpractice in trying to obtain that disclosure information, then it's possible to activate retrospective sanctions and to stop that person or group from using DataSHIELD again. Finally, a sensible prevention issue is, rather than putting DataSHIELD actually into the data warehouse, which would open up the risk that if someone did manage to hack it, then they would be able to immediately then get into other real data, the main data sets. We instead suggest that the Opal server sits somewhere in the environment of the data warehouse, but not directly connected to it, and behind the same firewalls that the data that normally are held in the data warehouse are sitting behind.